Hello, everyone. So it's almost 4. We'll start the class in a few minutes once a few more people have joined. And I'll just set up the class till then. So I had given a question in the previous class, which I asked everyone to solve, and I said I would discuss it in the next class. So this was a question on preferences, utility, and marginal rate of substitution. So there are 3 people, Sarah, Simon, and Rachel, and we're trying to discuss their preferences for 2 different ice cream flavors. One is butterscotch and the other is dark chocolate. Okay, so we are given some information about how much each person is willing to trade butterscotch for dark chocolate. You could frame it the other way around, but this is just how the problem is currently set up. If you want to, change the whole thing and change 1 from X to Y, the whole logical reasoning will still be the same. The expression is going to kind of flip, because we are being asked MRS D comma B, right? If we want to flip it to B comma D, the answer is going to be obviously different. So that said, I don't want to confuse anybody. We're just going to go with whatever is given to us. So we are told that Sarah is willing to forego 2 butterscotch to obtain 1 dark chocolate. Simon is willing to forego 1 butterscotch to obtain 3 dark chocolates, and Rachel is indifferent to dark chocolates, but she loves butterscotch. So all of them do this maintaining the same level of utility. Now, this is obviously important because although even if this is not stated in the problem, this is kind of understood that they're trading without any loss in utility. Just give me a moment. Okay, so let's plot this, or let's see what we are given. So we had asked the MRS of each person as MRS D comma B, which means D is on the x-axis and B is on the y-axis. question 9. Okay, so first, let's do this step by step so that we know exactly what to do if you're given another question of a similar type, and we go from the diagram to the value of the MRS, and from the value of MRS, we can of course do many other things which I think are not required in this question, but we could do. If we were given, say, the price of butterscotch and dark chocolate, we could also find an optimal bundle, for example, which is why this question is important even for this week's content, because this week we are going to do the next thing, which is utility maximization and optimization of preferences. Okay, so let's draw this diagram. First, for first person given is Sarah, right? So let's draw this for Sarah. This is D and this is B. Okay, now we are not exactly told what their utility function is. So I'm not saying that the curves are going to be flat or they're going to be curved in this way or they're going to be curved in that way. But whatever I'm drawing right now is just like the simplest case to illustrate to illustrate the concept, because if I draw very complicated curves, it's going to become a bit confusing. Okay, so I'm just going to draw straight lines for now, even though it's not necessary that they will be straight lines, because we are just told one point of their entire preference mapping. At one point, this is how they are trading dark chocolate for butterscotch. We don't know if this is what they always do. That's not what's given. Okay, so let me go to the question once again. So Sarah is for going to butterscotch. So let me draw it as just a simple line. So here you have 2, okay, and here you have 1. So if I just draw it like this, you can write the expression for MRS as minus delta y by delta x. Also, you can write it as in terms of marginal utility, or you can write it in terms of how much you're substituting one for the other, right? So MRS here becomes minus 2 by 1 is just minus 2. This is for Sarah. So I'm just showing the difference here. I'm not drawing the entire indifference curve mapping or anything. This is just delta. I'm just marking delta y and delta x. Or if you want, you can write this. It's the same thing as writing delta b upon delta d. If you don't want to use x and y, because we've used x and y. We've given d and b for x and y axis. Okay, so this is for Sarah. Let's go to the next one. Simon. For Simon's preferences, we are given Simon is willing to forego 1 butterscotch for 3 dark chocolates. Okay, so this is again D, this is B. So this is, say, 1, and this is 3. So you have something like this. Delta y is equal to 1, and delta x is equal to 3. So now we can just write MRS is equal to minus delta, sorry, not D, B. So now delta B is 1 and delta D is 3. So MRS for Simon is minus 1 by 3. It's not minus 3. Right. Now let's do the last one for Rachel. So now we are told for Rachel that Rachel is indifferent to dark chocolates, but she loves butterscotch. So she's not exactly willing to trade anything for anything, right? That's what she means. That, she doesn't care about dark chocolates at all. She only likes butterscotch. So here, this could be any value of delta y. We don't know the value, and we know that for delta d, she would not want any d, right? So let's say you can say delta d is this. MRS is minus delta b for delta d. Now, what we know is that um, Rachel would never give up dark chocolate for butterscotch. That we are given. We are not given the values of butterscotch or dark chocolate, but then we don't need it because we're already told that Rachel would not care about dark chocolate at all. So if she doesn't care about dark chocolate at all, she's definitely not going to give up butterscotch for dark chocolate. So this becomes zero, right? She's not willing to give up butterscotch. Or if you want to look at the other way, you can say delta B is equal to 0. Or you can say delta D. Okay, my delta and D and everything is looking same. Delta D is equal to infinite, which means she's willing to give up any number of dark chocolates for, say, 1 unit of butterscotch. That is the other way of looking at it. That even to gain, say, 1 unit of butterscotch, because she doesn't care about dark chocolate, it's useless for her. So she is willing to give up any number of dark chocolate for butterscotch. So either way, whichever way you like to think about it, her MRS is going to be 0, right? So that kind of covers all the options, and we are asked which of the following statements is or are correct. So let's go back and see what we computed. So for Sarah, her MRS is -2, so option C is correct. Simon's MRS is -1/3, so option A is not correct. And Rachel's MRS is 0, so B is correct. So you have only B and C as the correct options. Okay, so this was the question from last week, which we which we left, which I had said that we would cover. So now I will start with the questions for this week. If anybody wants to ask any questions, you can can ask me now before I start discussing, and otherwise I will just go ahead. Somehow attendance is a bit low today. I don't know why, but yeah. So I'll leave the question on the screen for a few minutes. Let me just post a reminder for the class, and I will discuss it once you had time to read it. Okay, so we are given this question where we are given Vasco's utility function. It is 10x squared into z or z, whichever way you like to pronounce it. You are given the price of x as $1 and the price of z or z as $20. And you're given his income, which is $300. And you are asked what would be his optimal consumption bundle. And this is not specific to this question as such, but in general, when you're asked optimal consumption bundle or bundles, like it would help to remember that in some cases that you can have multiple optimal consumption bundles, because there can always be a corner solution. Now, in this case, does it look like you will have a corner solution? You can't, right? Because if X or Z, either of them is zero, utility is going to be zero, and zero cannot be the highest utility the person can achieve, right? So there's not going to be a corner solution. So Z is equal to zero is definitely not going to be an option, because no matter how much you consume of X, without Z, your utility is still zero, right? So this is like option C is very out and out not the correct answer, but we'll solve for the correct answer. So I will first, like using this question, I will first illustrate the the general process we will be using for all questions on utility maximization. Now, in utility maximization, there are three ways of solving the same problem. One is like two of them will use calculus, and the third way is, I think, also like you would still need to use calculus maybe at some point, but the third way is if you do MRS equal to MRT. Actually, yeah, like all three will use calculus, but just in different ways, and it's like in different it will have different levels of difficulty. So let's solve this. So the first way is we just do MRS equal to MRT, right? And then we use that condition, whatever we get from MRS equal to MRT, and we use what that condition or that relation between X and Z to then satisfy the budget constraint, which is given to us in the form of the price and the income. That is one method. And we'll try to solve this question, or at least some other question, using at least one of the three methods. The second is that given the given the budget constraint, you find a relation between X and Z, or X and Y, whatever. In this case, Y is actually income, so X and Z, and you use that condition to plug in the value of X or Z in terms of the other variable into the utility function, and then you use differential calculus and you take partial derivative of U to maximize U. That is the second method to do the same problem. And the third method is using the Lagrangian or Lagrange multiplier method, in which we optimize a function of two variables given the constraint. It's a problem on constrained optimization, like a typical method for constrained optimization. So in this case, the constraint is the budget constraint, and the function which we want to maximize is the utility function, right? So we take U as the function which we need to maximize, and we write the Lagrangian using the budget constraint. And then, of course, we simplify, take partial derivatives with respect to X, Z, and lambda, if lambda is the Lagrange multiplier of the Lagrangian, that is. And we use whatever relations we get from there to solve for X and Z. I've just told you these methods orally right now, just to give you the bird's eye view of the three ways in which you can approach the same utility maximization problem. Now, I'll solve this one using any one method. If you have a preference, you can tell me which method you want to use. Otherwise, left to me, I will solve it using any one of the methods. And we have other types of questions in this. We will come to different methods in the remaining questions. So before I go ahead, any questions so far? Okay, I'm guessing no. So I'll go ahead. Let me run this. Right now we are given the function xz square, or yeah, sorry, what is it? 10x squared z. Okay, and we are given px is equal to 1, pz is equal to 20, and the income y is 300. Okay. So first, let's just write the budget constraint. So we know what we're working with. That is px into x plus pz into z is equal to y. Okay, px is 1, so this is just x plus 20z is equal to 300. Okay, that is your budget constraint condition. You can name this as equation 1. Now, if you want, like for the first problem, at least, I'm not going to use Lagrangian. And we will solve some other problems using the MRS methods. I'm not using that method either in this. I'm just using a simple variable substitution method. I don't think that's like the standard name of this method, but I'm just calling it a variable substitution method. So using this budget constraint, I will solve for x in terms of z, okay, which is pretty simple. You can, from here, you can see that x is equal to 300 minus 20z, right? So by doing this, what am I doing? I'm just assuming that the budget constraint will be satisfied, because if you think about it, no matter how much high utility I may want, I can still have only as much utility as my budget allows. So no matter what the maximum utility I eventually end up with, it will always have to satisfy the budget. And that is a condition which always has to be ensured when you're answering what is the maximum utility possible or what is the optimal consumption bundle for this person. Right now, how you, of course, arrive at the answer is going to depend on the method, and what answer you get will be dependent on the functions, blah, blah, blah. But this constraint always has to be satisfied in one way or another. And in each method, we will see how we are satisfying this constraint. So this is the way in which we are satisfying the budget constraint when we report X in terms of the income and the other variable. So now we can just rewrite the utility function. So we are substituting for X, okay, for X, not for Z. In terms of Z, U is equal to 10X square Z. Or I don't know, okay, I think this is going to be a little messier if we substitute for X. So maybe we can just substitute for Z instead. Let me simplify this. Sorry. Because X is in square, so we are better off substituting for Z. 300 minus X divided by 20. Okay, so we are substituting for Z, not X. U 10X square into Z. This you can cancel, and you can just rewrite this equation. Something like that, if you want, whichever way, or this is actually not even needed. This is not needed. So for maximization of, oh, this is x cube, sorry. Yeah, I knew I'm missing something. 10x square minus x cube. And this by 2. So all I've done is just a little bit of simplification. I multiplied the expression in the brackets by x squared, and 10 and 20 become equal to half. So this is 300x square minus x cube by half. Now what we want to do is we want to take the partial derivative of u with respect to x. So for utility, we'll take del u by del x, and we take the partial derivative with respect to x. So x square partial derivative is 2x, and the whole expression is divided by 2. So 2 and 2 cancel. So this becomes just 300x minus x cubed by 2. X cubed by 2 becomes 3x squared by 2. This is equal to 0. This is what we get from taking the partial derivative. Now we can just simplify it whichever way we want. So one solution is x is equal to 0, which is not possible. Why is it not possible? Because that gives you utility equal to 0. So that is not possible. Next, other option is x is equal to 300 into 2 by 3, which is x is equal to 200. So we get x equal to 200, and using this, we substitute the value of x into the expression for z. Z is 300 minus x by 2. So this is 300. So you get optimal if you want, you can write it like this. You can use x star and z star as the optimal consumption bundle. So are we given options? Yes. So did I do something wrong? I think I've done it right. Let's go back to the expression for z. Oh, this is by 20, not 2. Okay, sorry. Then this is 5. Yeah, because the options are 20 and 50 and 205, and I was wondering what I did wrong. So, right, if you see z is equal to 300 minus x by 20, and we just cancelled that 20 with the 10 later on when we were writing the utility expression. That's why I forgot that it's not 2, it's 20. When we substitute the value of x, it becomes 300 minus 200 by 20, which becomes 100 by 20, which is 5, right? So the optimal bundle comes out to be 200, 5. And that is one of the options, which is option B in the question. So option B is the optimal bundle. Okay, so let's go to the next question, which is again a similar kind of an expression, but we are not solving the same kind of a problem in this question. Slightly different. So in this question, we are given that DIGO has a utility function of u in terms of b comma z is equal to a b to the power alpha and z to the power beta, where a, alpha, beta are constants, b is burritos, and z is pizzas. Now, if the price of burritos PB is $12 and the price of pizzas is PZ is $10, and Y, which means his overall income or budget, is $600, then what is DIGO's MRS? So for now, we are just asked MRS. I think, is there any other question? Yeah. So the same question, we will have another part to it later on. For now, we just asked what is the MRS. So how do we calculate the MRS? MRS is nothing but ratio of the marginal utility of DIGO with respect to the two goods. And that's why we are given u b comma z, which means you can take b as x, on b on the x-axis, z on the y-axis, or b as good 1, z as good 2. So mostly it will always be specified in some form as to which is good 1 and which is good 2. It's not going to be left to you. If they have not specified which is good 1 and which is good 2, then when you're writing your answer, you should explain which you are taking as good 1 and good 2. But otherwise, mostly it will always be specified which is good 1 and good 2. Okay, and you have to look in which form it is specified. Like sometimes it will be given with the MRS, sometimes with the utility, or sometimes you will be asked MRS of this with respect to this, something like that, right? That's your hint, that's your clue as to which is to be good one, which is to be good two. Okay, so let's solve this. This is question, oops. This is question 2. Let me write the expression. So we have D goes utility. All you're asked is MRS. So first let's find marginal utility, or you can say marginal utility with respect to B is the same thing as writing U subscript B. It means, let me write it like this, del U by del B. You're taking a partial derivative of U with respect to B. So this becomes A alpha B to the power alpha minus 1 Z beta. Similarly, we take partial derivative of U with respect to Z, and this is A B to the power alpha into beta into Z beta minus 1. Therefore, you can now find the MRS, which is minus B, U minus UB by UZ. I'm just putting the expressions which we just got for UB and UZ, nothing fancy. And there's a minus sign here. Okay, now what can we see? A is getting cancelled. We are left with minus. Alpha and beta we can clearly see. You cannot cancel alpha and beta. Now what we are left with is B to the power alpha minus 1 in the numerator and B alpha in the denominator. So I was just solving this. We have B to the power of alpha minus 1 upon B to the power of alpha. So that is 1B in the denominator. And similarly, we have Z to the power of beta in the numerator and Z to the power of beta minus 1 in the denominator. So we have 1Z in the numerator. So your final expression becomes minus alpha Z upon beta B. Okay, this is looking very... Okay, so this is the answer. And let's see what options are given. Yeah, so you have 3 options, and the answer is what we just got, minus alpha z by beta b. And the minus is just for our sort of understanding that you're giving up one good for the other good. So the minus is not included in the answer. You just ask the value of it. Okay, so in the same question, you are now asked what is Diego's optimal bundle. And we can do that thing in the same way. So for this, let's go to question 3. Now we know the MRS expression minus alpha z upon beta b. And open the question again. Yeah, so you are asked his optimal bundle, which you will obviously need to report in terms of the constants A, alpha, and beta. And we are given the budget constraint as PB into B plus PZ into Z is equal to Y. PB is 12B plus PZ is 10. This is 600. So this is given as your budget constraint. Now we can sort of solve for it if you want. You can solve for it, but otherwise, let's just do it the simple way. We can find the MRS equal to MRT relation. MRS we already know. MRT is what is the price given to us? 10 and 12, right? So MRT is, sorry, just give me one moment. Yeah, so MRT is going to be PB by PZ, and PB we are given as 12, PZ we are given as 10. So from, when we say that MRS is equal to MRT, what we are saying is that the optimal consumption bundle is satisfying the equation of both the curves, the budget constraint as well as the utility maximization, that is the indifference curve. So we are given MRS as, now let's remove the minus sign, we're just going with, because this minus minus is going to cancel, it's alpha z by beta b is equal to 12 by 10. So now from here what you can do is you can find one variable in terms of the other, right? This is like, the same thing we did before. If you want, I can solve it, but I would actually prefer it if you solve it yourself. But anyway, I will solve it. So you are given, let's say, what are we given as the utility function? A, B alpha, beta, B beta. This is going to be an ugly expression, but okay, let's try. Okay, this is the value of Z, and let's plug this back into the expression for U, which is A B to the power alpha, and this is the value of okay. You can simplify this a little bit. This whole thing, let's say this is equal to K. So we can just write this expression as K times B to the power of alpha plus beta. Okay. So it's like a slightly ugly algebraic expression, but we take partial derivative. Now, for this, we like simply solve this. This is not really so alpha and beta are positive constants. K is also a positive constant. So K is greater than 0, alpha comma beta are greater than 0. So therefore, b to the power of alpha plus beta minus 1 has to be equal to 0. So if you want to take this in terms of log, you can take log on both sides. You can say alpha plus beta minus 1 to log b is equal to 0 is equal to log 1, right? So what we can say is alpha plus beta minus 1 is equal to 1, which means alpha plus beta is equal to 2, which is a condition on the parameters, or okay, I'm not sure if this is actually needed, but this yeah, this is not needed actually. Oops. This is not needed. If oh, if b is equal to 1, then we have the solution. Then uh, log 1 is equal to 0, right? So this becomes equal to 0. You don't even need to write this actually, just 0 is enough. Right? Alpha plus beta minus 1 can be any positive number, but if b is equal to 1, then LHS is equal to 0, right? So therefore we get the answer b equal to 1, and you can substitute the value of b equal to 1 in the expression for z, and therefore you get z is equal to 12 beta by 10 alpha. Okay, it's a little complicated question, but I just wanted to show you all the steps of the question. So just go over it once again. If you have any problems, you can ask me. Just give you a few minutes to think over it. Okay, so this is how we solve these type of questions, and um, now we come to a slightly more fundamental aspect of consumer theory, especially utility maximization, where we are given that, if a consumer has like, for two goods A and B, if he finds that marginal utility with respect to A divided by the price of A is greater than marginal utility with respect to B divided by the price of B, then which of the following is true? So I'll give you a few minutes to think over it, and then I'll discuss. Okay, so this basically, I think I'll just illustrate this question. That way we can understand it better. So in any kind of utility maximization setup, you will have something like this. Like say, suppose this is your indifference curve, and say you have, okay, not here, this as your budget constraint. Okay, so we have something like this as the indifference curve and the budget constraint. And now we're just going to see what happens at different points of, the consumption set, let's say. So now what we know is that at this point, we are kind of assuming that MRS is equal to MRT. Now MRS is the slope of the indifference curve, and MRT is the slope of the budget curve, or the budget constraint, which is basically just price of X versus price of Y. So this is X and this is Y, A or B, whatever you want to call it. So say this is MRT is constant, as you can see, Px by Py, right? You can put a minus here. And MRS is equal to marginal utility with respect to X versus marginal utility with respect to Y. Now, at this point, at the point of tangency, the very fact that this is a point of tangency means that the slope of both the curves is going to be the same. Mathematically, that is what we know. Now, intuitively, what we mean is that, say suppose there is this one point here. At this point, we draw something else. At this point, the curve is something like this, right? This is how this is the tangent at this point, okay? And at this point, the utility is like basically the same, but at this point, the budget constraint is not satisfied, right? And you can also see that, let's call these different points something. Say, suppose this is point, I'm out of symbols. Let's say this is point P1, this is point P2. Okay, at point P2, or that consumption point P2, you have a lot more of Y in the consumption and very little of X, right? At this point, what is the consumer going to want to do? He's going to want to maintain the same utility level, but he will want to be within the budget, because this point is making him like kind of happy, but it is outside his budget constraint, right? The budget set is only inside this, or on the line, inside it or on it. This is the budget set, right? And this point P2, even though it is giving the person, the consumer, the same level of happiness as point P1, it is outside the budget. So what is the guy going to want to do? He will want to forego some of the Y and consume a little more of the X. So he's sort of, coming closer to point P1. Now, another way of looking at it is, you can see marginal utility with respect to Y upon price of Y versus marginal utility with respect to X upon price of X. Now, at this point P2, what we know is that MUX divided by MUY is greater, right? And the slope or whatever is anyways given, the Px by Py is constant, so that we already know. So you can see that this line is steeper, right? The blue line. So that means that he is going to get a higher utility by substituting y for x. So he's going to move towards point P1. And hence, without foregoing too much without foregoing any of his utility, he can still come within the budget set or budget constraint. Therefore, intuitively, what we mean is that, as long as the ratio MUX upon PX is greater than the ratio MUY by PY, it is feasible for the person to go on consuming more of X and substituting Y away from his consumption bundle, substituting Y for X or removing some of Y and taking in a little more of X, right? Now, I'm just saying the same thing in 2-3 different ways. So as long as this is like this, he will consume more of X. This is basically the same thing as saying MUX by MUY. This is the same thing as MRT. And this is the same thing as MRS. Okay, so as long as MRS is greater than MRT, you're going to consume more of X, right? But if this flips, then you will consume more of Y. Now let's look at some other point on the same curve. So this is point P3. At this point also, he is having the same level of utility, but he is consuming a whole lot of X and very less of Y, and subsequently he is kind of outside the budget set again, right? So now he is going to want to shift towards P1, which means he is going to consume less of X and more of Y. So you see, there's like a trade-off going on until his marginal utility, the ratio of his marginal utility with respect to X and Y is exactly equal to the price ratio. So this is kind of what we are trying to say, that, as long as MRS is equal to MRT, the person is going to consume more of good X or good 1. And if MRT is greater than MRX, the person is going to consume more of good Y or good 2, whichever way you want to look at it. And at the point at which MRS is exactly equal to MRT, he is in a balanced position. He doesn't want to trade anything for anything because he has achieved the maximum utility possible and he's also within the budget constraint, right? Does this make sense? Or you have any questions? Okay, so this is the, let me go to the question since some of you have joined a little late. The question was, when a consumer has MUA by PA greater than MUB by PB, which of the following is true? And the options are that, should he consume A and B in the same quantity? Should he consume more of good A? And should he consume more of good B? So obviously, in this case, the person should consume more of good A, which is option A. Now we'll do a similar question a little bit numerically. So we are given, you've studied quasi-linear preferences in your lectures. We're given that a consumer has a quasi-linear preference given by the utility function ax plus b root y. Now, you're given the prices of good x and y as px and py respectively. All you're asked is what is the condition for optimal consumption of goods x and y, which means at the point at which the budget constraint is satisfied and you have achieved maximum utility possible with your given budget, what condition is getting satisfied or fulfilled, or what algebraic expression can you reduce the preferences to? So if you want, please take a few minutes to solve this and then I will solve it. It's a very easy question, especially after discussing question number 4. So I will just mute myself for 2-3 minutes, not that long, and just to give you guys a chance to solve this first. And then I'll solve it myself. So let's try to solve this question. We are given that okay. Okay. This is the expression for utility. The price of X is Px, price of Y is Py. Okay. So because we're given the prices, we know that MRT is just basically Px by Py, and I'm kind of ignoring the sign here. Just give me a minute. I'm ignoring the negative sign here because we're not really going to use the negative anywhere. So I'm just removing it for now. Okay, and we need to now find the MRS. MRS is equal to marginal utility with respect to X and marginal utility with respect to Y. Wait, let me rewrite this. Okay, this is actually capital X and capital Y. So X, Y. Okay, so let's calculate the marginal utility with respect to X. We are given the expression AX plus B root Y. So marginal utility with respect to X is just A. Okay, and with respect to Y is now B root Y. If you take partial derivative with respect to Y, let me write that. It comes out to be B upon 2 root Y. So therefore, you get MRS is equal to A 2A root Y upon B. I've just divided MUX by MUY and I've taken 2 root Y to the numerator. This is pretty simple. Therefore, condition for optimal consumption is MRS. MRS is equal to MRT, which is PX by PY, is equal to 2A root Y by B. And if you want, you can simplify this. You can see which all options are given. Like this expression can be written in 3 different ways. So if you simplify this, or if you rearrange the terms, you will see that both option C and option D are correct. This is the final answer. This is the condition for optimality. Okay, so I will take a short break here, and after I come back, we will solve some more questions on utility maximization. And I'm trying to take similar type of questions because at your level, you're not going to solve too difficult questions. And if you want, I can do one which is similar to what's in your assignment. I'm trying to not do the same thing which is in your assignment. Just trying to show you the reasoning which you should follow in your assignments. Okay, so I will leave this question on, and I will just be back in 5 minutes. And in the meantime, this is like similar to whatever we have solved till now. So please try to solve this yourself, and then I'm going to solve it. Okay, so this question, question 6, I think it's from one of the books, either Perloff or Van Dyke and Ruben Field. I don't remember which one exactly. I picked it last year, so I don't remember which book it is from, but it is from one of the books. And I think it has some other parts also in the book. So if you want to go through the question, you can do that. One of the earlier questions, the one with Digo and um, burritos and pizza, that is also from a book, I think from Perloff. I don't remember exactly, but yeah, I've also modified some of the questions, so I do not exactly what they were in the book. So anyway, I just wanted to let you know in case you want to go and practice some of these questions, stuff like that. Okay, so we are given Linda loves buying shoes and going dancing, right? And her utility function for pairs of shoes, S, and number of times she goes dancing per month, T, is U, S comma T is equal to 2ST. Okay, so basically she has some budget, and in that budget, she can buy a certain number of pairs of shoes, which is S, and she can go dancing per month for a certain number of times, or number of classes, you can say, because maybe let's assume she's doing dance classes or something for which she's paying. So the number of times she can go for dance classes is T. So it costs Linda $80 to buy a new pair of shoes or to spend an evening out dancing. So, you can think of it as some kind of a admission fee for a dancing kind of place like a club or something, or you could think of it as dance classes. It's not specified, but it costs basically to go out dancing. Now, assume she has $1280 to spend on shoes and dancing. That is the budget she has allocated for this activity or these two activities. What is Linda's marginal rate of substitution, MRS, of S comma T? This is a very easy question, actually. Let me just rewrite the function again. Now we want to find MRS. Now let's first find marginal utility with respect to S. This is 2T. Let me rewrite this, explaining it a bit. So this is del U by del S, therefore it is 2T. MUT is del U by del T is 2S. Therefore, MRS. Again, I'm removing the minus sign because that is not like really significant in these calculations. Is marginal utility with respect to S, marginal utility with respect to T. It's 2T by 2S, therefore it is T by S. So option 1 is the answer. Now the next question in the same question is to find her optimal bundle. Now we are given that MRS is T by S, and we are given the price also, so we can find MRT, which is price of S upon price of T. Price of S is 80, and price of T is also 80. So both have the same price. That's what's given. It costs Linda $80 to buy a new pair of shoes or to spend an evening out dancing, which means both the activities or both goods are exactly the same price. So PS by PT is equal to 1. Therefore, this part kind of becomes simple. Then MRS is equal to MRT and is equal to 1. So T by S is equal to 1, which means T is equal to S. So now that we know this, we can use this condition in the budget constraint to find what she exactly does, right? So we know the budget constraint PS into S plus PT into T is equal to, say, her income. Price of S is 80 S plus, say, PT and T are again the same price. So let's remove one variable, just use one variable, 1280. So therefore, this becomes 160 S is equal to 1280. S is, I think, 8, right? And this is also equal to T. So therefore, so this is your optimal bundle. And this did not take us very long to solve because we are given that the price is the same. And because the price is the same, we simplify the expression a lot, and we did not need to use any more calculus or any more complicated expressions. Just by knowing that one condition, we substituted for S, and we just simplified the expression, and you get the answer. This is the optimal bundle, basically. Now we'll go to the next question. Let's do it this way. Okay. So this was question 6. Now let's go to question 7. We've already solved question 7, and we have like one last question remaining, which has several parts, and I'll solve all the different parts of the question, but it's also like important to understand how we can solve these questions if they are combined with the concepts you have already learned, which are like quite a few. Okay, so now we are given that Maria likes baked potatoes and corn on the cob. Okay, now I have actually created this question so that you kind of also learn sort of simple principles which we have used in our chapter on demand and on the chapter on taxes. And in the same question, if we want, we can also introduce a kinked budget constraint, and then we can see how the optimal budget, the optimal consumption set is going to change, right? So I'm not making it too complicated right now because you don't have to solve questions at that level, but I'm just explaining how you can reconcile what we are studying now in consumer theory with what we have already covered in the demand curve and taxes and all of that, budget curve, blah, blah, blah. Okay, so her utility function from consuming both is given by U is equal to A, B, C, where A is a positive constant. Okay, and she has only $30 in her pocket. Okay, this is like on any given day. I'm not talking about just one time, but any given day, she has only $30 in her pocket. Now, corn on the cob costs $5 per unit. Let's just say it does. I don't know what it costs in the US right now, but let's just say it may not necessarily be US dollars for that matter. It could be any other dollars. But say this is some dollar, it's $5 per unit, and baked potatoes cost $8 per unit. Now, assume that the constant, is equal to 2. Now, what is her optimal consumption bundle? That is the question. So, thought somebody messaged something. Okay, so the first part is pretty straightforward. We are given the price of both the goods, we are given the utility function, and we are just asked the optimal consumption bundle. So let's solve this part. This is okay, and we know her income is 30. Price of the corn is 5. Price of baked potatoes is 8. A is equal to 2. Now we can write Budget constraint, this is PC into C. This is 5C. This is pretty straightforward so far. Okay, so now instead of again, I'm not using the Lagrange multiplier method because I think that is a slightly more advanced method of calculus. If you want, I can solve it again in Lagrange method and I'll add it to the notes later on. But for now, I'm not using that. I'll just substitute for C in the expression for the utility. 2B into C. So this is 2B into 30 minus 8B by 5. So utility becomes you can write it like this. Okay, I've just simplified the maths. 30 by 5 is 6. 6 into 2 is 12. So 12B minus 16B square by 5. Now we do the utility maximization. We just need to simplify this. Therefore, B is 60 upon 32, and we can calculate this. This comes out to be 1.875. Okay, now we know the value of B, we can compute the value of C. C is equal to 30 minus 8B by 5. This is 30 minus 15 by 5. This comes out to be 3. Okay, so this is the value of B. Therefore, okay, let me highlight this because we will use this later. Okay, now let's go back to the rest of the question. This is this is the optimal consumption bundle. Now, we know that if due to a bad crop, the price of corn on the cob increases to 10. Earlier, corn on the cob was 5. Now, corn on the cob is increasing to 10. What is her new consumption bundle? Now, obviously, we will solve it just like how we solve it right now. We will solve it again using the value of PB as $10 instead of $5. But the bigger thing to understand here is if you relate this whole part of the question to what we studied earlier in demand and supply. Basically, this is nothing but if there's a bad crop, the supply curve is shifting, right? The demand is the same, but because the supply curve is shifting and there is less corn being supplied, what is going to happen to the price of the corn? It's going to increase, right? So this is what is happening here. And I have simplified this question by just directly giving you that the price of the corn on the cob due to a bad crop is $10. But what could also be done is that, say, suppose you are given the demand curve and the supply curve for corn on the cob in the market demand, market supply curves are given, and then you are told that this is what happens to the supply curve. Then you will have to find out the new equilibrium price, right? You find out how the supply curve is shifting. Based on that, you find out the new market price for corn, and from there you can, of course, solve the rest of the question. So I'm not making the question as sort of complicated, but I'm just trying to make you get an intuition for what are we really doing here, and how our everyday consumptions or everyday choices change based on these market forces, based on these everyday happenings which are happening. Like, there are times, especially in India, I'm talking about, like, there are times when sometimes onions are really expensive, sometimes potatoes are really expensive because of a bad crop, and sometimes tomatoes are really expensive. So, how we alter our consumption bundles based on current prices, given our budget, blah, 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 we change how much we're consuming different goods to achieve the same level of utility, which is what we are doing here. So you see, let me just also draw the diagram for this, just so we, know what we are doing. And I'll draw the diagram again after the changed pricing. So this is the type of the function given is like u is equal to a and b into c, which is sort of like a hyperbola. The indifference curve is of the form xy is equal to constant, or xy equal to k, which is the curve for a hyperbola, right? So let's draw this indifference curve. Okay, this is a bit difficult to draw it on an iPad, but something like this, okay? So no matter how well I draw, the lines always look shaky on an iPad. And I found out that is not my handshake, that is just how the screen is. There's nothing you can do about it, apparently. Anyway, so now say suppose our budget curve is something here, right? And these are the indifference curves. So now let me mark the point. This is the initial consumption bundle, which is what are we taking this as? This is B, this is C, and this point is, let's say 1.9 comma 3. Okay, 1.875 is almost 1.9. So I'm just writing 1.9 comma 3. Okay, this point. Okay, now what we are told is that the price of corn on the cob is increasing, right? So once the price of corn on the cob increases, your budget is going to change, which means this green line is no longer your new budget constraint. Your new budget constraint is going to be something different, right? Some other line. And how do we know that it's going to be okay, this drawing is not very good. Let me first draw this diagram properly again, because otherwise I am going to run into trouble. Okay. So suppose this is the energy budget constraint. This is okay, it's still not going to come out. I don't know how to make the two curves parallel. Okay, so this is not going to be on scale, but yeah, it's not going to be on scale. Okay, I will have to redraw this. Hang on. I will draw the indifference curves later. First, let me draw the new budget constraint. Okay, so let's first see this. This is the original consumption bundle. Okay, 1.9 and 3. This was 1.9 and 3. And we'll solve for the next consumption bundle just from common sense. You can see it will come out to be 1.9 comma 1.5. So I think my proportions are wrong. Let me draw this again. No, wait. Now let's draw a hyperbola. And this is a different hyperbola where I have to try to make it tangent at a very different point. Something like this, okay? This is also not exactly accurate, but this is your original consumption bundle. And let me not draw this. This is wait a minute, let me redraw this. Okay, something like this. Yes, this is correct. Takes a little bit of a while to get these curves right because I don't want to draw it showing something which is not correct. Okay, now let me just explain it once again what I have drawn. So green is the original budget line, which is what we just solved, and this point where it intersects the first blue curve is the original consumption bundle. Let's call this P1, and this point is P2. P2 is the consumption bundle we will get after change in prices of corn, and the new budget constraint, let me write this part, is given by pink line. Okay, so the new budget constraint is given by pink line. You can see that only the intercept on the y-axis has reduced. The intercept on the x-axis has not changed because there is no change in the price of baked potatoes. I'm just recapping and revisiting all the concepts we have covered till now in this one question, at least to some extent. Okay, so we can solve the same question all over again in the same way. Let me do that very quickly. What was given to us is rewriting. Let me rewrite the budget constraint. So the price of corn on the cob is now 10C plus baked potatoes are the same is equal to 30. C is equal to 30 minus 8B upon 10. So instead of 5, it is 10. Again, we substitute it into this curve. You solve this, simplifies to, you can say this simplifies to 3 into 2, 6 b square minus this is 8b by 5. Instead of 16b by 5, this is 8b by 5. Del u by del b is equal to 12b minus 8 by 5 is equal to 0. B is equal to, did I do something wrong? No, B is equal to, no, I did make up some, oh, this square is wrongly placed. Sorry, this is what? 2b into, yeah, this is square. Yeah, that's what I thought. There's something wrong. This is what happens when you do calculus a bit too fast. Let's do this again. So this is just, we've substituted for C, which is 30 minus 8b by 10 multiplied by 2b. So this is 30B, not 6B, sorry. 3, no, this is 6B, sorry. Yeah, 30 into 2B by 10. 30 by 10 is 3, 3 into 2 is 6, this is 6B. The rest is correct. Now we take the partial derivative. This is 6 minus 16B by 5. Therefore, B is equal to, oh, why did I write B here? 5, yeah, 30 by 16. And this comes out to be what? I think this comes out to be the same, right? B comes out to be the same. And what we need to calculate is C. C is 30 minus 8B by 10. So just from common sense, you can see that instead of 3, we will get, okay, let's solve this actually. 30 minus 8 into 1.875 by 10. This comes out to be 15. 15 by 10 is equal to 1.5. Therefore, new consumption bundle is B star comma C star is equal to 1.875 comma 1.5. Okay, this is the new consumption bundle. And this is what I have drawn. This is what I've sort of represented here on the diagram, that consumption of B is remaining the same. This is 1.9 or 1.875. C was initially 3 and C is now becoming 1.5. So this is how you can visualize it on the diagram. I mean, the diagram cannot be like more clear. Actually, I've tried my best to show you the diagram. And obviously the utility is going to be decreasing if you're reducing C without increasing B. You're keeping B at the same level, you're reducing C, so obviously there's going to be loss in utility. So this point is going to be on a new indifference curve, which you can see is the case. So the first point P1 is on an indifference curve which is higher up, and point P2 is on an indifference curve which is a bit lower, right? So I hope this is clear. Let's go back to the question. Let's see what else is asked in the question. So this is if due to a bad crop, the price of, okay, this we have done. Next part is, now most of the potatoes and corn are imported where Maria lives, right? Now due to new tariffs on imports, Maria now has to pay an additional tax of $1 per unit of good. And now what is her new consumption bundle? So for this additional tax of $1, we can refer to the original case, not the revised prices of $10 or whatever. The $5 and $8, we use that and we add an additional tariff. So more than just solving it mathematically, I just again want to emphasize what is really happening in this particular situation. So now here I have just again given you that, this is $1 per unit of good. But if you are given the, say, the demand and supply curves in the market, for the different goods, for potatoes and for corn. So suppose you're given the market demand and the market supply, and then you're told that the government is imposing this much tax on, and it is legally, on the buyer or on the seller, whichever way. Then you can calculate consumer tax burden, right? How much of that particular tariff or tax or whatever is falling onto the consumer and how much is falling onto the producer, right? So you can find the new price for the consumer if you are given all these things. I've not done that because again, I don't want you to feel like it's too complex and you don't know how to do this, but this is what we've just discussed 2 weeks ago in the tax chapter, right? So if you're given the market demand, market supply, and the new tariff and who is supposed to pay it or whatever, If you know the market structure, you can compute the consumer tax burden or the new price to consumer or new price to producer. This case, you only need the price to consumer. So instead of this $1, you can compute what that consumer tax burden is going to be. So anyway, I just wanted to illustrate that. So I gave these questions. Let's solve this also quickly, and we can also draw the diagram. When there are tariffs, it was originally 8, right? So this is 9, and PC is say 6. Okay, we are not increasing it after 0.2. We are just saying on the original prices, there is an additional tax burden of $1 per unit. Okay, so this becomes the new price for the consumer. So now again, we do the same thing. U is equal to 2 BC. We write the budget constraint again. Okay, this is actually divisible by 3, so you can just simplify this equation. Okay, this is the budget constraint. You want, you can label this. C is again equal to 10 minus 3B by 2. U is equal to 2. B into C is now, you can cancel 2 and 2, so you get a slightly neat expression now. Take partial derivative. 10 minus 6B is equal to 0. Therefore, B is equal to 10 this is what, 5 by 3. This comes out to be how much? Oh, come on. Okay, this is 1.67. And if you want to simplify the expression for C, this is 10 minus 3 into, let's say, 10B by 6. It's much easier to solve this way. 3 by 6 is 1 by 2. 10B by 2 is 5B. 10 minus 5B by 2. Wait, what? No, this is not 10. Okay, so this is your new consumption bundle now. Now you can see there is a change in both the quantities, not just one quantity. And this is nothing but revision from your previous previous classes. Now let me draw this on a diagram. So initially what we had was the original pricing. B was 1.875 and C was 3, right? Now C has reduced from 3 to 2.5 and B has reduced from 1.875 to 1.67, right? So both have reduced. So we'll draw the curve accordingly. Say this is your original budget constraint. Now you have a new budget constraint, which is not exactly the same curvature, but something like this. Let me draw the indifference curves. So if this was your original consumption bundle, this is like something like this, not this, wait. It's a little bit extreme, but I mean, if I make it a small difference, it is not going to be obvious how. Okay, so these are both your two indifference curves. This is tangent here, and this is tangent here. Okay, so this is your original consumption bundle, and this is your new consumption bundle. So you can, oh no, sorry, wait, this is a bit wrong. Hang on. This x has to reduce, it's increasing in our current setup. So it's maybe somewhere here. Okay, so this is, say, suppose the new point of tangency. It's again not so obvious, but you know, you can only draw so much. So you can see that this is the new x, this is 1.67, and this is the new y, this is 2.5. This was originally 3, and this was originally, say, 1.9. So your consumption has shifted to the left, and it has shifted to the left and to the down. So it has shifted to the next indifference curve, which is, you know, satisfying the new budget constraint. I'm just drawing this so, you know, we know exactly what is happening, and you know, how you reconcile the new budget with the same utility function. So basically your utility is decreasing, right? Because you're reducing the consumption of both the goods, and you cannot hold utility constant as long as you're decreasing the consumption of both the goods. And that is because prices of both have changed. Because prices of both have changed, the x and y intercept both have changed. Like in the, if you compare it with the initial curve, compare it with this, you can see that in this only the y-intercept has changed, but in the new one, both x and y have changed. Okay, so so that is all there is in this question. If you have any other questions from this week or previous weeks, I can answer that. Otherwise, you know, I can end the class here. So we still have like about 15 minutes to go, but no, I finished all the questions and brought to the class. So yeah, just one more thing, like, you know, just be mindful of one thing, that, you know, if you have a constraint optimization problem in which instead of like these budget, or instead of money or income, you're given time as the constraint. And it can be because, you know, it's a similar setup, right? You will use exactly the same kind of logic. So instead of $30, it may be number of hours per unit as the expense. That will be like the price of that particular goods. For example, if we go back to this question of Linda dancing, if instead of money, the constraint was time, and if you were given that instead of the $1,280 she has to spend on shoes and dancing, we were given, she has only 8, let's say 8 hours, 4 hours, whatever, to spend on shoes and dancing. So, you know, she can either spend time shopping for shoes, or she can spend time dancing. So she can dance in 1 hour, 2 hours, and we take both as continuous variables, of course. So instead of optimizing for, you know, the quantity based on constraints for pricing and money, we optimize for the quantity based on time. So if you can say that it takes Linda 1 hour to buy a new pair of shoes, and it takes her the same amount of time to finish one class or one unit of, whatever way you're measuring dancing, 1 unit, 1 class, 1 hour, whatever. So you do the same kind of a optimization problem. It is not any way different from whatever we have done. And let me see if I can find that question. Just give me a minute. So let me just quickly solve this Linda problem once again with time. I did it last year and I'll just take that up because we have a few minutes left. So we are taking time constraint. Let's say y is equal to 6 hours and you say ps is equal to 1 hour, pt is equal to 2 hours per unit. Whichever way you want to measure that unit, 1 hour of shopping or 1 hour for shopping for one pair of shoes, for certain pair of shoes, or whichever way you want to see it. Okay, then you become, then your PS by PT is equal to 1 by 2 and MRS was still T by S. Function is the same. Okay, utility function is the same. Therefore, you plug in, say 1S plus price is 2T is equal to 6. 6 hours is the constraint, right? And instead of T, we can substitute for T. Therefore, we can say half is equal to T by S. Therefore, S is equal to 2T. Therefore, instead of T, you can also substitute for S. So S we plug in 2T plus 2T is equal to 6. T is equal to 6 by 4 or 3 by 2. And therefore, S is equal to 3. So this can become your new optimization bundle. Therefore, I've just taken the same example as what I took last year. I didn't write it down, but it's the same example. So I'm just illustrating how if time is a constraint, it is still solved the exact same way. If instead of PS and PT is equal to 1 hour, 2 hour, if I taken it as 1 and 1 hour, you would get the same answer. I mean, not the same answer, but similar answer to what we got before. S is equal to T would be value. Okay. So, I mean, you can solve it the same way as what we did before. So I think the concept is clear now. We don't need to worry too much about it. It is the same method. If you want me to solve anything using Lagrange method, I can do that, but I'm not purposely not including it because it's slightly advanced and I think at your level you guys don't use Lagrangian. So you can just stick to the simple methods and it's pretty straightforward. Okay, so since I think I have covered everything from today's class, I will end the class here. There's a reading list at the end of the lecture notes. You can refer to that. And there are a lot of questions in all of these books. You can practice it there. Okay, so I'll end the class here and I will see you again next week.